Good morning, all. Today we are going to learn about Turing machine. See, in the previous classes, we have learned finite automata and push-down automata. In the Chomsky hierarchy of languages, we have seen regular languages and context-free languages. Regular languages are accepted by finite automata, whereas context-free languages are accepted by push-down automata. And we have a new called languages accepted by Turing machine. Example for recursively enumerable languages which are accepted Turing machines are A power and B power and C power and WW. You have to know that regular language is subset of context-free language and context-free language is subset of recursively enumerable language. So Turing machine can able to accept recursively enumerable languages, context-free languages and regular languages. So these recursively enumerable languages are accepted by the machine called Turing machine. Can you recall finite automata? In finite automata, you can able to see, you can have infinite input tape and the tape head. Whereas in Turing machine, you have infinite input tape and the tape head. Here the tape head is read-write head. It can able to read as well as write the symbols over the input tape, and it has a finite control. Similarly, we have learned about push-down automata. In push-down automata, you will be having an infinite input tape and the read head and finite control. Along with that, you will be having stack. But in Turing machine, we don't have stack, but instead of stack, you can able to store the content in the input tape itself. It can able to read the input as well as you can write something over the tape. Okay, so this tape is divided into number of cells and each cell can hold one symbol at a time. So this is about the Turing machine structure. Okay, so there is no, when we talk about this tapes of Turing machine, there is no boundary for it and it is infinite in length. Okay, and it has a read write head. The head can able to read as well as write. But previously we have learned this finite automata and push-down automata. In that we'll be having a head called a read head able to read the difference is that this read write head can able to move in both the direction. It can able to move left as well as right. So this read write head can able to do these operations at a time. It can able to read a symbol and also can able to write a symbol. Okay, so rewrite the content which it has read, and also it can able to move left or right, either left or right. So we'll see example for that. So for example, if you have A, B, A, C at the input tape at the time 0, and if you want to write A into K, then look at the time 1 diagram. Suppose suppose you are reading A, and if you want to rewrite it as K, and if you want to move left side, so in the next time, so at time 1, this A is replaced by K, and the tape head is pointing to the left position of this cell, so where you can able to find B. So reads A, writes K, and moves left. We'll see another example for movement of right side. Suppose you have A, B, K, C. The previous step you had A, B, K, C. So now you want, suppose if you want to replace this B by F, and if you want to move right. So this is how your configuration will look like. When you read B, you are supposed to write that B, rewrite that B as AF and move right. So when you move right, the right hand side symbol pointed by the read right head is K. Okay, it reads B, writes F over it, and the tape read right head is moved towards right. Okay, then we'll talk about the input string in the Turing machine. Okay, so since you have infinite input tape, you can place the input string anywhere in the string, but the tape head, the read write head will point to the first symbol of the valid input string. Suppose you have A, B, A, C as the input string, and before which you have an n number of infinite number of blank symbols, and afterwards you have infinite number of blank symbols, because this tape length is infinite in nature, isn't it? So but your tape head points to the first symbol of the input string. So tape head starts at the leftmost position of the input string. Always, if there is any valid input string, then the at initial state, the pointer or the tape head or the read write head is pointing to the first symbol of the string. Then we'll see about the state and its transition of Turing machine. Okay, you know that you have to use a circle to represent states, and double circles for representing a final state or accepting state. Now, you should have a label over the transition, which is nothing but the symbol which is read by the uh, Turing machine head, and next you should have an arrow mark. Then you have to have the symbol which is used to rewrite over this A, and the movement of the tape read write head. So here you can able to see Q1 to Q2 is a transition. Okay, when you read A, then what you have supposed to do, the machine should rewrite this A by B and move left. And in this diagram you can able to see, when you are in state Q1, when you read A, then change that A into B and move right side. So we'll see some examples with that. Okay, at time T1, you have A, B, A, C in the input tape, but the current state is Q1, and the tape head is pointing to the third input symbol A. If so, suppose if you want to replace that A by B, and if you want to move right towards, then the turn like right head is pointing to the right symbol. So the right symbol is C. Look at here. Uh, Previously it was AB, AC and the state is Q1. But if you have a transition Q1 comma A is equal to Q2 comma B comma R, I mean you want to replace the A by B and move the head right side and the state must be changed to Q2. Look at here at time 2 you can able to find out that A is replaced by B and the state is changed from Q1 to Q2 and the tape head is pointing to the right symbol, that is C. Clear? Suppose if you want to move left and if you want to change the A into B and if you want to move left, this will be the configuration. So at time T1, ABAC is on the tape and the read write head is pointing to A and the state is Q1. And then A is supposed to be changed as rewritten as B and the tape head should be moved left side. So left side symbol is B and the state is transited to Q2. Clear? Suppose if you if you have a transition that Q1 comma epsilon is equal to Q2 comma G comma R. I mean if you are reading a empty symbol or blank symbol from the state Q1, then you have to write G and you have to move right. If so, at time T1, you suppose you are pointing at a blank and you are in state Q1. And time 2, what you are supposed to do, you have to rewrite that blank into G and the tape head should point to the right symbol of this G, that is a blank. Okay, and the state must be changed as Q2. Okay, and we know that we have learned about deterministic finite automata and deterministic push down automata. Similarly, we have deterministic Turing machine. Okay, shall we recall a deterministic finite automata? When will you call the finite automata as a deterministic finite automata? For a straight, for each and every input symbol, if there exists only one next state, then we'll call that as deterministic finite automata. Whereas in non-deterministic finite automata, for a state, for an input symbol, there may be 0 or more transitions. For an input 1. So in push-down automata, you have to satisfy 2 conditions. Can you remember that? For a current state, for a current input symbol, there should be only one transition. As usual, we have talked about the finite automata. And one more thing you have to add with the deterministic push-down automata is that if you have a transition for a valid input symbol, you should not have a transition for a epsilon. Or else you can say, otherwise, if you are having a transition for a epsilon, you should not have a transition for a valid input symbol from the same state and the same stack symbol. Here we have deterministic Turing machines where allowed and not allowed content will see. Here also there should be only one transition for a input symbol. Okay. So you cannot have more than one transition for the input symbol. Here you can able to see from Q1 for A, it can able to change it as B and can move right. And for the next input symbol B, it can convert it to D and it can move left. For the same input symbol, there should not be a two different transition which is not allowed. And also very important thing, no lambda transitions allowed. Epsilon transition is not allowed in case of deterministic Turing machine. Epsilon transition is not included in the deterministic Turing machine. Okay, and partial transition functions are allowed. Okay, that is, no transition for an input symbol is also allowed. For example, in the tape, you have a string A, B, A, C, and the input head, that is tape read write head, is pointing to A, and the state is in Q. The transition that you can able to see from Q1, there are two transitions for A and B, but there is no transition is mentioned for C. So partial transition is allowed. The partial transition is allowed in Turing machine. You have to remember that. And we'll talk about halting in the Turing machine. When will you see the machine is halt? A machine halts in a state if there is no transition to follow. If there is no transition to follow, then we can say the machine halts in that state. Okay, we'll see one example. Suppose this is the configuration. The machine is in Q1 and currently pointing to C, but from the transition diagram from Q1 there is no outgoing edges are present. I mean, when you are in state Q1 and when you read anything, you won't make a transition, so that the machine will stay in Q1 itself. So this is called halting. It is not accepting, but the machine gets halt because no transition is mentioned from this Q1. Okay, we'll see another examples. Similarly, here also you have an input string A, B, A, C, and the current state is Q1. From the current state Q1, there are two transitions mentioned. One is for A, another is for B, but there is no transition mentioned for C. So what will happen when the machine is in state Q1 and when it reads C? It will not make a transition. It will be in the same state. Okay, the machine stays in the same state Q1 and it halts because there is no transition is mentioned. The Q1 is not the accepting state, so you can conclude the string is not accepted. The machine halts. Okay, then we'll talk about the accepting state. Okay, usually we'll be mentioning the accepting state or the final state by the double circle. And here you should have a condition that there should not be any transition out of accepting state. Accepting states have no outgoing transitions. The machine halts and accepts them. Whenever after reading the entire input string, you are halting at the final state, then you can say the string is accepted and it has halted. Okay, so acceptance. Accept input string, reject input string. Okay, you can say after reading an input string, the machine can able to see whether the string is accepted or rejected. So whenever you see the string is accepted, the machine halts in the accept state. When you say the string is rejected, if the machine halts in a non-accepting state, or the machine enters into an infinite loop. Okay, in order to accept the input string, it is not necessary to scan all the symbols in the string. Okay, you have to remember, you no need to read the entire string in order to say it is accepted. Okay, when the machine can halt the final state for any input string you have given, then you can say the string is accepted. This is an example for that. Input alphabet sigma is equal to a comma b accepts the language A star. So this is a Turing machine which is designed to accept A star. So you know A star is a regular language, and Turing machine can able to accept the regular language also, because the regular language is subset of recursively enumerable language. Turing machine accepts recursively enumerable language. Okay. So A star in the sense 0 or more A's. Okay, look at this transition diagram, the Turing machine. From the state Q naught, when you read A, keep that A as H, but move right and go through all the A's. When you read a blank symbol, keep that blank as blank, but move left and enter into the state called Q1, and Q1 is represented as a final state. Okay. So, how does it work? We'll see. At time 0, that is initially, uh, suppose you are having input string triple A, and the machine should start from the initial state Q naught. So, after reading A from the state Q naught, the machine moves to the right side, so it can point to the next A and it stays in the same state. Okay, so here Q naught comma A, again it should stay in the same state and it should move right side, and again it reads Q naught A. So the state is Q naught and the input symbol read as A. It has to move rightward without writing anything on the tape. Okay, so now Q naught comma blank. So Q naught comma blank. Then what should be taken place? So the next state must be Q1, and the blank should be kept as a blank, but the head should move left side. Head should move left side. The state is Q1 and the input symbol pointing by the tape head is A, but look at here, we are not coming at the end, we are pointing to a symbol A, but that is we didn't complete we cannot say that we have completed the input string, because we are here now, here you are pointing at A, but you are halting at Q, and then you can say the string is accepted. Okay. Then we'll see the example for rejection. Suppose you have A, B, A as an input string. Initially, Q naught is the initial state and which is pointing to A. So Q naught comma A is you have to move forward. So Q naught comma B, but Q naught comma B, there is no transition is mentioned. Okay, so the machine cannot able to move further. Here this Q naught, the machine gets false, but Q naught is not a final state. So Q naught is not final state. So here your machine halts and announce the rejection. Okay. And a simpler machine for same language but for the input alphabet A alone. Okay. So you can say this is the Turing machine which A star. epsilon. It can able to epsilon. It can able to, if you give A, what will happen? It will be in the same state Q naught, and it is announced as final states, and you can say A is accepted. Okay. So what happens if you give a triple A? Look at here. Q naught comma A. So Q naught comma A, it will not make a move, but it is in the final state, isn't it? So if the machine is in the final state, you can say it is accepted. So no need to scan the entire input string. So we'll see another example for infinite loop. Okay. So far we have seen examples where the machine halts at the accepting state for the string which belongs to, and halts at the non-accepting state, and which is a string not belonging to that. So that is we called as rejection. So we'll see another example for infinite loop. So now here you have a Turing machine which is designed to accept A star plus B into A plus B the whole star. So what is the meaning of this language? Either 0 or more A's are a string which starts with B and followed by any strings of A's and B's. Okay. Suppose if you want to check whether the string ABA is accepted or not. Okay, so first we'll see from the state Q naught for the input symbol A, what happens. Okay, so it should move right side, and it should stay in the same state Q naught. Okay, from the state Q naught for the input symbol B, what should do? Whenever it reads B from the state Q naught, it should move, the machine should be in the same state, but the tape head should move to the left. Okay, next it points to A. So what will happen? So whenever it reads A, so it will do like this. It will come forward, and it will read B, and again after reading B it will go backward and it will read A. So this will be repeated for n number of times. Okay, so this is an example for infinite loop. Because of the infinite loop, the accepting state cannot be reached. The machine never halts. The input string is rejected. Okay, and we'll see another example for the Turing machine. So here you are given, this is previously we have seen a regular language A star, and we have designed a Turing machine for that. Now we are going to see a Turing machine which is going to accept the context-free language A power n, B power n, such that n is greater or equal to 1. Okay, how can you design a Turing machine for that? So start from this Q naught. So when the algorithm, so replace the leftmost A with X, find the leftmost B and replace it by Y. You have to repeat this operation until there are no more A's or B's. If there is no remaining A or B, reject. Okay. So look at here. You have to start with this Q naught. When you read A, you have to replace it by X and move right. Okay, and move and make a transition to Q1. When you are in Q1, if you read A or Y, you keep that A as such or Y as such, but move right until you find a B. When you read a B, you have to convert it to Y and move left. While moving left, when you read A or for any number of time you have to keep as such but move left. While moving left, when you read x, what you have supposed to do, you have to keep that x into x but move right and repeat this operation until you find y. So while moving right, when you cannot able to find a, suppose you are finding y, you keep that y into y and keep move forward. That is move right and go through all the y, and at the end you can able to find a blank symbol. Suppose if you are finding a blank and you keep that blank as blank and move left and halt at Q4. Okay, we'll see one example for that. How does it work for the input symbol or not the input symbol, an input string AABB. Okay, so as usual, the machine starts from the Q naught, the initial state, and the first symbol of the input string A. So Q naught comma A, what happens? Okay, so A has to be changed as Y and the state is changed to Q1 and the input head is pointing to A and Q1A do nothing forward, okay, and stay in the Q1. And Q1B, what you are supposed to do? Q1B change that B into Y but move left. While moving left, if you find A, don't do anything but keep on moving left. But you are in state Q2, if you find X, what you are supposed to do, you have to move forward. While moving forward, you repeat the operation, that is change the A into X and a B into Y. So this A is changed into X and move forward. And if there is Y, meanwhile keep Y as Y but move forward. So now you have got B, so convert it to Y and move backward and make a transition. And when you are in Q2, when you read Y, you have to move backward. When you read X, when you are in state Q2, what you have supposed to do, you have to move forward. While you are moving forward, if you are finding Y, then you have to keep that Y into Y but move forward until you find a number. When you are in until you find the blank, what you are supposed to do, you have to enter into Q4 and move left. So here Y is pointed by the read write head, but Q4 is the final state or halting state, the machine gets false here. Okay, and you can able to modify this same transition diagram in order to accept the language A power n, B power n, C power n. How can you do that? You need to introduce one more state, that is Q. For suppose if you have till Q4 here, you have to introduce one more state Q5, and where you can able to convert C into Z, and you have to add more transitions related to this C and Z. Okay. Now we'll see the formal definition for Turing machine. So far we have seen the basics and the transition diagrams of Turing machine. Then how can we define Turing machine formally, mathematically? Okay. So you know transition function. So transition function of Turing machine takes two arguments and returns three values, triples. Okay. So it takes two arguments. What are the two arguments it takes? The current state and the current input symbol, and returns three values. What are the three values it returns? The next state and the symbol which is used to replace, or which is used to rewrite over the tape head pointing, and the movements of the heads of rewrite head. Okay, so that there are 7 tuples in the Turing machine. Finite set of states Q, finite set of input alphabets sigma, finite set of tape alphabets gamma, del is the transition function, Q naught is the initial state, and a blank symbol, and the final state, finite set of final states. So there are 7 tuples. Whereas in finite automata we have 5 tuples, Q, sigma, del, Q naught, F. But additionally we have 2 more tuples which are tape alphabets and blank. Because here we can able to write something else over the tape. But in finite automata we can able to read, but here we can able to write. So this gamma is a superset of sigma. Okay, sigma is subset of gamma. Next we'll see about the configuration. Suppose you have CABA in the input tape, and Q1 is Q1 is the current. So how do you represent this while uh, as an instantaneous description? So here instantaneous description is represented as a string. Okay, so it has 3 components. The string which is left side of the the head, and the current state, and the um, right side of the pointer, including the current input symbol. So look at here, CA is the string which is at the left hand side of this read write head, and BA is a string where B is the current input string and A is the right side of this B. Okay, and Q1 is the current state. So instantaneous description is represented as a string which has 3 components. You can call it as alpha, beta, gamma, and the alpha is the leftmost string. Q1 is the beta is the Q1 here, Q1, which is beta is used to represent the current state, and BA is in BA, B is the current input symbol, and the remaining is the leftmost, sorry, rightmost string from the current symbol. Okay, now we'll see. Suppose at time 4, the state is Q2 and it is pointing to X. Okay, and you have A, Y, B at the right hand side. So how can you represent it as an instantaneous descriptions? So at the left hand side you have blank, so no need to mention it. But Q2 is the current state, and the input head is pointing to X, and the remaining is A, Y, B. Okay. Suppose at the time T5, the head is moved to the next input, the right input symbol, and the state is changed to Q0. How can you represent that? That is, leftmost string is X, the current state is Q0, the remaining string is A, Y, B, where A is the symbol pointed by the read write head. Okay, suppose you have some four sequence of transitions. How can we represent it? So Q2 X A Y B. This X Q naught A Y B. This is XX Q1 YB. This is XXY Q1B. This is how you can able to represent the instantaneous description of the Turing machine, which is nothing but the moves of the Turing machine. Okay, so this sequence Q2 XAYB uh, transition move to X Q naught A Y B, next transition X X Q1 Y B, the next move X X Y Q1 B. This can be rewritten like starting with the initial configuration, that Q2XAYB, then you can have the instantaneous description symbol over which you can have the star, then you can have the final configuration, that is XXYQ1B. So what is the meaning of this star? 0 or more moves. Okay, here you have some set of moves in order to reach from this configuration to this configuration. It is the equivalent notation. Okay, so always the initial configuration should be like this. You have to start with Q naught and followed by the W, the input string. Okay, for example, here Q naught is the initial state and the input string is AABB. Okay, next we'll learn about the accepted uh, language of Turing machine. So whenever you say the language is accepted by the Turing machine, for any Turing machine EM, the language accepted by the Turing machine, which is denoted as L of M, is equal to some set of language W such that Q naught W over the multiple view move x1 qf x2, where this qf belongs to capital F, that is finite set of final state, and q naught is the initial state. So starting from the initial state, after following this W, the machine should halt at the final state. Kindly understand, the machine, the Turing machine should halt at QF. QF belongs to capital F, finite set of final state or accepting state. The language L is accepted by the Turing machine M, then we say that L is Turing recognizable. Okay, whenever the language is accepted, then we can say the language is Turing recognizable language. Other names used are Turing acceptable language or recursively enumerable languages. Recursively enumerable languages. In Chomsky hierarchy of languages, we have seen the hierarchy. Regular languages are subset of context-free language, and context-free languages are subset of recursively enumerable languages. Recursively enumerable languages are nothing but Turing recognizable languages. Okay, now we'll see how can we use a Turing machine to do computation? Okay, so if, do you know function? So function maps domains with a region. Suppose f of w. So that you are giving and you are giving, and it makes transition uh, to some region. So you will be getting the result after performing the function over the input string. A function may have many parameters. We'll see one example for that. Addition function. So here f of x comma y. So there are two parameters passed to that addition function. So what will be the result of this addition function? Will be getting x plus y. When you pass two input string x and y, you will be getting the output as x plus y. Okay. So, in case of Turing machine, it is good to represent numbers in unary format. Okay. For example, uh, 5 is the binary number. Sorry, 5 in binary you can represent like 101, but in unary you can use 5 ones to represent. 5 ones or 5 zeros, that is Yavish. Okay, we prefer unary representation easier to manipulate in the Turing machines. So function f is computable if there is a Turing machine m such that it can switch from the initial state to the final state where you can give the inputs in the initial state and you can get the output from the final state. In other words, a function f is computable if there is a Turing machine m such that q naught w over the multiple transition, it can be in the state qf and we can able to get the f of w, the final configuration. Clear? Now we'll see example where you will be doing addition operations. So for that, the input string is x0y. Since you have used ones to represent the numbers are the inputs x and y, you can use the 0 as a separator of this x and y. And the output may be x followed by y and the separator, the separator 0 at the end. How can we do it? So initially you have to represent x and y in the input tape and you have to separate them with the 0. And initially q naught is the initial state and the tape head will point to the first symbol of x. Okay, so you have to remember 0 is a delimiter that separates the two numbers, two input symbols. So 0 is a separator we are going to use to separate the two input symbols. Okay, how can you get this final configuration? At last, we are supposed to get this ones together. The number of ones present in x and y together. At last, you are supposed to get one. You do it. So this is the Turing machine which can able to perform the addition operation which we are talking about. So what you are supposed to do, you have to go through all the ones in the x and move right. When you reach 0, you are supposed to convert that because you have to get the number of ones continuously. So in between you have a 0, the separator 0. You need to convert that 0 into 1. Then move forward. Yeah. And you through. I'll show you the configuration so that you can understand it. So this will be the initial configuration, and this should be the final configuration. What can we do? So go through all the ones and convert this 0 into 1 and move forward till this blank. So when you find a blank, what you are supposed to do, you have to come back and convert the last one into 0, because you have added one extra instead of this 0, and you have to change the last one into 0. That is what represents in this diagram. Look at here, go through all the ones and convert 0 into 1. Again go through all the ones and come to the blank and move left. Then convert the last one into 0 and move left and go through all the ones. Okay, and that is your coming back to this configuration. See, look at here. uh, this is how we have taken as the final state. So the input, the read head should point to this one and it should halt at Q5. That's what in this diagram you can able to find. From this Q3, you have to go through all the ones and you have to move right until you find the blank symbol. When you find a blank, you have to keep that blank to the blank, but move right and halt at the Q4. Clear? So we'll see execution example. So x is equal to 1 1. So that is used to represent number 2. Y is equal to 1 1, which is also used to represent number 2. Okay. So the initial configuration. So x and y should be separated with 0 and the initial state is q naught. So q naught is in q naught, we are the machine points at 1. Okay, and this is the final configuration. Okay, so we'll see how does it work. At Q naught, when we read 1, you have to keep that as 1 and move right. Okay, and at Q naught, when you read 1, you have to keep that as 1 and move right. When you are in Q naught, when you read 0, what you're supposed to do, you have to move to Q1 and you have to change that 0 into 1 and move on. Now we are in state Q1. When you read 1, you have to move forward. When you are in Q1, you have to move forward. When you are in Q1, when you read blank, what you are supposed to do, you have to come. You have to move to state Q2 and move left. Okay. So when you are in Q2, when you read 1, you are supposed to convert it to 0 and move left. When you are in Q3, when you read 1, you have to move forward. Okay, again Q3 1, move forward. Q3 1, move forward. Q3 1, move forward. Q3 blank. What you are supposed to do? Go to Q4, that is the halting state, and move right. So this is the final configuration we have considered. So here we have computed x plus y. We have taken x as 2 and y as 2. Now we have got the answer as 4. Clear? Similarly, you can also able to perform this operation 2x. Okay. So where x is the integer, you have to pass it as the input, and the output string you are supposed to get as xx. Two times of x you are supposed to get. Okay, so how can you start? You have to start the initial configuration with the number of ones which is mentioned in the x. But at the final state, you are supposed to get 2 times of x. Okay, and this is the algorithm you can use. Repeat every one with dollar. Sorry, replace every one with dollar and repeat this function. Find a rightmost dollar, replace it to one, go to the right end, insert one until no more dollar remains. Okay, we'll see the example. Okay, so Q naught, when you read 1, replace with dollar and move right. When you find a empty symbol, a blank, then you keep it as blank, move left and convert what you are supposed to do. In Q1, when you find 1, you have to keep it as 1 and move left. When you find a dollar, you have to uh, convert that dollar into 1 and move right. Okay. And you have to repeat this operation until you find the blank. We'll see one example. So starting state, uh, Q naught. Suppose you are giving the input as 2, that is 2 ones. Okay. So Q naught. So just work out this as a homework, and if you have any doubt, you can clarify me in the next class. Similarly, you can also do more operations. So here you have given with another function f of x comma y is equal to 1 if x is greater than y, to 0 if x is less than y. Okay, and result. If x is not matched, erase the tape, right one. Else erase the tape, right.